Okay, so today we'll continue with the 5.3, 5.4, and 5.5. 5.3 is self-inductions. Okay, now before we look at self-induction, let's do a quick recall on what is the induced EMF. Induced EMF, okay, EMF is equals to negative d flux over dt. So it means that whenever there is a change in magnetic flux, then there will be an induced EMF. Okay, it is being produced due to the change in flux. Now, what does it mean by change in flux? So you have to remember, what does it mean by flux? Flux means if you are given a cross-sectional area, the numbers of line passes through this cross-sectional area that will give you a flux. So flux equals to BA cos theta. So if there's a change in any either variables in these equations, then it will lead to a change in flux, and therefore EMF will be induced, okay, in the coil or in the solenoid. So now if you look at these self-induction, what is the difference between self-inductions and the induced EMF that we have seen in the chapter 2 and so on? Okay. Okay, guys, can you hear my voice or not? I think there's some issue with my mic.
A bit. Like
okay, wait, yeah. Nothing else. Now, is it better?
Yes, madam.
All right, cool. Okay, so before that, in 5.2, we have seen what is an induced EMF, and we've learned how to generate it. Now, in 5.2, if you remember, the things that involved in the questions is just the magnet. Okay, what happens to a magnet? What have you done to a magnet? And then you move the object inside a magnetic field and so on. Okay, so you are changing the area, you are changing the B, and you are changing the theta through what I would say motion. Okay, you move the coil, and then you change the surface area through external force, and then you move a magnet towards it or move it away from your object. So that is what happens in 5.2. In 5.3, what are we going to see? Now we're going to try to manipulate the current. So initially in 5.2, okay, for example, we have a solenoid. We are playing with either moving this piece of magnet close toward it or moving away from it, okay, to change the magnetic field line passes through the solenoid. In 5.3, what are we doing? Okay, we no longer use a piece of magnet, but we use current to generate magnetic field across the solenoid, okay, through the solenoid. So self-induction process, now it involves current. Okay, it is the process of producing an induced EMF in the coil due to a change of current flowing through the same coil. So how to change the current? We change the current by manipulating the variable resistor in our circuit. So now consider a solenoid is being connected in a series to a battery. Okay, so this is our normal EMF. Okay, EMF coming from a battery. That is not induced EMF. So when it comes to self-induction process, we have two types of EMFs right here. The first one is the regular EMF that is coming from the battery. And then we have a so-called induced EMF. Induced EMF is also known as back EMF. Okay, the EMF that opposes the changes that has induced it. That one we call back EMF. Now back, it doesn't represent the direction. Okay, so usually students have a misconception. When they look at back EMF, they thought the terms back means they are in the opposite direction. No. Okay, that is not the case. Back EMF is just simply means that, okay, it is an EMF that's being induced due to the change. Okay, due to the change in your circuit, the change of current. So now we have EMF, induced EMF, or sometimes known as back EMF. And then also we have a normal current that is being generated by the power supply, or induced current that is being induced due to the induced EMF. So we have two different set of information in induction process. All right, so the normal one coming from the battery and the one that is because of the changes. the induced set because of the changes. So now consider a solenoid is connected to a battery, okay, and a switch and a variable resistor. Okay, we must use variable resistor. The reasons I will tell you in a bit. And forming an open circuit as shown in the figure below. Okay, so now let's see why. Okay, what is the reasons? Why do we need a variable resistor? So when switch S is closed, a current, it begins to flow in the solenoid. The current then produces a magnetic field whose field line through the solenoid and it generate magnetic flux linkage, because now definitely you have more than one turns. Okay, solenoid takkan satu turn saja kan. So you have more than one turn. That's why it uses the terms magnetic flux linkage. So when switch S is closed, magnetic flux linkage will be generated across the solenoid. So by using your right-hand grid rules, okay, you then found out that the north pole is on the right-hand side and the left pole is on the left-hand side. Okay, left, yeah, north pole on the right and south pole on the left. So step number one, okay, step one, the first thing that you should do, look at the diagram, determines the directions of I. Okay, determines the directions of I using the terminal, the EMF, okay, using the battery, based on the terminal of the battery, using the terminal of the battery. So you look at the battery and then you determine the directions of the current. Okay, so in this diagram, obviously your current is flowing in the anti-clockwise direction. Okay, anti-clockwise direction. So you use terminal of the battery to determine the directions of the current, which is from positive to negative terminal. Oops. To negative. And then step number two, okay, step number two, you then determine, okay, determines the position of north pole by using right-hand grid rules. Okay, you need the positions of the pole in order to determine the directions of induced current. So you start from step number one, and then step number two determines the positions of the pole. And after that, we will learn how to determine the directions of induced current. But right now, let us go back to the diagram and see what happened. So point number E. So after you switch on the power supply, magnetic flux is being generated. Now you have north pole on the right-hand side and south pole on the left-hand side. And if the resistance of the variable resistor changes, that's why you need variable resistor right here, because you want to manipulate, you want to change the values of resistance. So you change the value of resistance, and what is going to happen? It will then change the values of current. Why? Because we have equations V equals to IR. In this case, we have EMF equals to IR. Okay, where the EMF is coming from your battery, your power supply, of course, your source. And the battery comes with a fixed potential difference, right? It comes with a fixed EMF value. Therefore, what happens right here is, now you have I is equals to EMF over R, meaning that I is now inversely proportional to your R. So when R changes, I changes. Okay, so this one, when R changes, I also changes based on the equations VIR, right? So you're using variable resistor and you have a fixed EMF. Therefore, when R changes, I changes. And what happens when I changes? So if I changes, then so does the magnetic flux linkage. Why? Now try to recall what is the relationship between I and B. In chapter 4, we know that B equals to mu naught Ni, okay, in which B is proportional to I. Therefore, when I changes, B also changes. Okay, B also changes. So that is what happens right here. Now, if B changes, according to Faraday's, what is going to happen? Now, according to Faraday's, okay, an EMF has to be induced in the solenoid since the flux changes. So because your B changes, so what happens next? We have flux equals to BA cos theta, where, again, phi is proportional to B. If B changes, okay, then flux changes. So according to Faraday's, what happens when flux changes? When flux changes, you have induced EMF. Okay, so that is what happens in self-induction process. So induced EMF is being generated, is being produced because of what? Because of the change in current in our circuit. So change in current, why? Because of the change in R. You're using variable resistor. Variable resistor means that the value is not fixed. You can change it, you can manipulate it. So change R, it leads to the I changes. Now I changes, what happened? It leads to the change in B. B changes, what happens? Now you have the change in magnetic flux. And according to Faraday's law, whenever there's a change of magnetic flux, then you have induced EMF. And once you have induced EMF, it will then produce induced current. Okay, why? That is because of your induced magnetic field. Okay, your B induced. Now let us see. After you have, okay, after you prove that there's a change in magnetic flux, after you know that, you find out that there's an EMF that's already induced in the solenoid, then how are we going to determine the direction? So according to Lenz's law, the induced EMF opposes the changes that has induced it. Okay, induced EMF opposes the changes that has induced it, and it is known as back EMF. So how to determine the direction? Now let us go to the diagram right here. So initially, okay, according to the original diagram, we have north pole on the right hand side and south pole on the left hand side. Okay, so north, south as shown in the figure. So if I increase, okay, so we have two cases. One is I increase and one is I decrease. If I increase, what is going to happen? So before that, now let me sketch a magnetic field line across the solenoid here first. Okay, so the solenoid here, we have a north on the right hand side and south on the left hand side, meaning that now my magnetic field line is from left to right. Okay, so this is a normal magnetic field line that is coming from the normal I. Okay, so this is the B. So now I increase. Okay, I increase, it means now B becomes stronger. B also increase. When I increase, the strength of the magnetic field line increase. Now, according to Lenz's law, it doesn't want to experience any changes. It will try to do something to oppose the change. So what is it going to do to oppose the change? Now, since your B in this diagram, it becomes stronger, meaning that a magnetic field line in the opposite direction will be induced, will be generated to oppose the change, because it doesn't want your field line to become stronger, to get stronger. So B induced is being generated in the opposite direction when I increase. Meaning that by looking at the green color line right here, okay, I'm going to use the highlighter to make it a little bit more obvious for you. Okay, so this is my green color field line. Green color field line and the green color field line. So green color magnetic field line is now coming from the right hand side and leave the left hand side. Okay, it's leaving on the left. So what does it mean? It means that now here it represents the north pole, the induced north pole, because your field line is leaving, is coming out. And on the right hand side, this would be your induced south pole, because your field line is entering the solenoid. So when it's entering the solenoid, then it represents south pole. When it's leaving, then it represents north pole. Okay, so step number 3. Okay, step number 3, you determine, okay, determine B induced, okay, or N induced north pole, induced north pole, your N induced, okay, determine N induced based on the change in the current. Okay, the change in the current. So if I increase, then what? Then N induced is at the opposite position. Okay, opposite to the original B. So your original N. Original north pole is on the right hand side. So because of I increase, now your N induced is at the opposite direction, at opposite position. So if your I decrease, then your N induced will be at the same position. Okay, that is your step number 3. Once you have the induced north pole, okay, step number 4, okay, you then determines the directions of I induced. Okay, determine the direction of I induced by using what? By using your right hand grip rule again. Okay, by using your right hand grip rule. But then one thing that you have to take note. Just now we determine the directions of north pole by using the right hand grip rule as well, right? But when it comes to step number 2, you use normal I to determine the positions of normal north pole. When it comes to induced current, if you want to find out where is your induced north pole, then if you want to find out where is your induced current, then you have to use your induced north pole. So in step number 4 right now, your thumb, it represents the directions of N induced. Okay, whereas the 4 fingers, it represents the directions of I induced. So that is the difference between step number 2 and step number 4. Step number 2, you use regular I to determine the positions of north pole, the regular north pole. All right. And then in step number 4, you use induced north pole to determine the directions of induced current. That is the difference. Okay, that is the difference. So once you find out what is the directions of induced current, then done. Okay, then you can describe. So for H, okay, for situations in H when I increase, your I induced is now flowing in the clockwise direction. Okay, in the clockwise direction. So that is how you determine the directions of your current and also the directions of your induced current, right? Now, sometimes students will ask me, how am I going to determine the direction, whether it's clockwise or anti-clockwise? You need a bit of imagination. Okay, now let's look at I. If you look at I, how am I going to know whether my finger should be going up or going down? Okay, you look at the diagram, the red color arrow. Red color arrow, it shows that on the right-hand side, it shows that it's going up and it is at the back of the solenoid. So you imagine it keeps flowing up at the back of solenoid, and when it reaches the front part, your finger is pointing downwards. The current is pointing downwards. So when you apply your right-hand grip rule, you hold this solenoid, okay, by pointing your 4 fingers downward at the front part. Okay, dalam exam, actually apa yang kamu kena buat, you hold a pen. Kamu ambil satu pen, and then biar dia menghadap, you put it in front of your eyes, you let it facing you, and then you hold the pen. You look at the directions of current. Just now, the eye is going upward when it is at the front of the solenoid. Okay, kalau dia bergerak ke atas, when you hold it, you let your 4 finger pointing upwards on the side that is closer to you. Okay, biar tangan yang menghadapi Anda. Kalau di case pertama, okay, you let the 4 fingers pointing towards you. Okay, pointing upwards. And then for the second case, you let your finger pointing downwards. Okay, so all right. So you're just imagining it as a pen. Okay, and then you're in front of the screen. So when you hold it, you look at the 4 fingers. Okay, whether it's pointing downwards or pointing upwards. So that is how you determine the directions of the pole and south. Okay, now when I decrease, what happened? So when I decrease, well, your magnetic field line is still pointing in the same direction. It doesn't affect the direction of the B, okay? But because I decrease, now your B decreased, okay? Your B also decreased. Okay? So your B decreased. What happens when your B decreased? B decreased now because it doesn't want to change, because the solenoid, it wants to oppose a change. So what happens right here? B induced will be generated in the same direction to top up the magnetic field lines that you took away from it. So now B induced is in the same direction. Therefore, it means that your N induced and your S induced, they are both located at the same position as your original pole. Okay, original north and south pole. So the directions of current, same as the current in the red color. Okay, so now your I induced and your I, both of them, they are heading towards the same direction. Why? Because your B induced will be generated in the same direction to top up the missing B. Okay, to top up the missing B that you took away from it because you changed the R. Okay, because your R, the resistance increased. All right, so basically that is what happens in self-induction. Okay, that is what happens in self-induction. So, well, I give you a few minutes to write it down. If you can understand what happens in self-induction, then it shouldn't be an issue for you to understand what happens in mutual induction. Okay, self-induction dengan mutual induction, konsepnya sama. The only difference is self, well, the name calls self. Everything is happening inside self. When it comes to mutual, then you have two solenoid. Okay, because mutual, it can't happen if you have just one solenoid. So right now, make sure you understand this case first, this process, this self-induction first. Okay, so I give you a few minutes to go through it. If you have any questions, please ask before we proceed to mutual induction. Okay, I would suggest you to write down the 4 steps in your book so that you know how to determine the directions of an induced current. And if possible, okay, if you got a different color pen with you or a highlighter, okay, try to sketch both magnetic field line in your diagram as well. Okay, so maybe the original one, you use pencils, and then the induced magnetic field, you use a pen. Okay, or you use pen for a normal B, and then you use pencil for the induced B. Okay, so that you can see, so that you can remember what happens in a self-induction process. Okay, even after you leave the class. So the 4th step is important in determining the direction, and then this is the relationship. Okay, this is what you have to mention in your explanation. Okay, this is what you have to mention in your explanation. So catat, jangan tak catat. Kalau kamu tengok saja tak catat, memang tak akan faham. Okay, so far so good. I hope you are okay. Okay, you are still with me. Okay, so yeah. Okay. So just now we're looking at the process. Okay, so now we're going to see how to calculate the strength. Okay, the strength of inductance in the solenoid. Okay. So self-inductance, just now we were looking at self-induction. Self-induction is a process, okay? It's a process. If you're going to look at self-inductance, then it tells you the strength, okay? How much energy can be stored in your inductor. So self-inductance is defined as the ratio of self-induced, or we say back EMF, to the rate change of the current in the coil. So equations L is equals to negative EMF over di per dt. Now, if you look at the definition, actually, what happens right here? We start from EMF is directly proportional to negative di over dt. Why? Well, EMF is being generated in the self-induction process due to the change in current over the time. Okay, and the direction, because it's always opposed to change, therefore we put a negative sign in the relationship. So from here, we then obtain the mathematical equations. EMF equals to negative L di over dt. So by looking at these two equations, okay, actually it tells us that L is a constant value in this equation, meaning that when di over dt changes, what is going to happen? EMF will change. It won't affect the values of L because L is just a constant unless you change the physical structure of the inductor. Okay, unless you change the physical structures of the inductor. Otherwise, L is always a constant value. Okay, it doesn't matter whether you change the EMF or the DI in your inductor, okay, in your solenoid. So it won't affect L. So isn't it, it looks very similar, okay, this concept, because, okay, the same things that we have seen in chapter 2 and also chapter 3. In chapter 2, we have V is proportional to I. In the mathematical equations, we have V equals to IR. So in these equations, what we have R is a constant value. Okay, R is a constant value. So the idea is the same. So in chapter 2, what we have is C is equals to, not C is equals to Q over V. Let us start from the relationship. So C, the definition of C is a V over Q, is Q over V. Meaning that in chapter 2, the things that we have learned so far is your V is proportional to Q. Okay, when you have more charges or when you have a more potential, higher potential difference, then it can store more charges. When we change it into mathematical equations, we have V equals to CQ. Okay, we have V equals to CQ, in which it shows us that C is also a constant. So these three electrical components, actually, they look very similar. Okay, their idea is very similar. They are all constant. Okay, and their definition is a ratio. For R, it is the ratio of V over I. For constant C, the capacitance, the definition is a ratio of Q over V. And when it comes to L, the definition is the rate change, is the EMF over the rate change of current in the coil. Okay, and all these three components, their reading is fixed unless you change the physical structure of the component. Okay, for R, it depends on what? If you remember, in chapter 3, we learned that R is equals to rho L over A. So either you change the length or the cross-sectional area or the material of the wire, then you can change the R. Otherwise, it is a constant value. When it comes to C capacitance, we have C equals to epsilon naught A over D. Okay, epsilon A over D, in which it depends on the material of a solenoid, of a dielectric, the area of the plate or the distance between the plate, which is also a form of a physical structure. Then when it comes to inductor, okay, when it comes to a inductor, if you look at equation for L for a solenoid, okay, L for a solenoid, how are we going to determine it? We'll look at it in the next page, but right now I'm just going to write it here for you. L is equals to epsilon, okay, N square A over L for solenoid, meaning that it also depends on the physical structure of the inductor. It depends on the numbers of turns, it depends on the cross-sectional area of the solenoid, it depends on the length of the solenoid, and mu naught again, it depends on the material. Okay, it depends on the material or the medium inside the solenoid. Okay, it depends on the medium in between the solenoid. So this is a solenoid. Okay, this mu, it shows a medium inside here. Okay, the medium inside the solenoid. So some solenoid, they will have a soft iron core, a piece of metal inside it. Okay, but in our syllabus, we assume it is vacuum. Kita anggap tak ada apa-apa di tengah-tengah solenoid. So these three electrical components, their idea is very similar. Okay, and the functions of solenoid is actually same as the functions of the capacitor. Is to store energy. Okay, now let us go back to the equation. So di sini saya cuma tunjuk Anda the similarity between these three equations. Okay, apakah persamaan antara tiga equations ini? The idea is exactly the same. Okay, the definition is just a ratio. What does it mean by ratio? Ratio means that if you change this thing, and this thing, it won't affect our constant value. And what happened? How are we going to change the value then? The strength then? We change it by changing its physical structure. Okay, its physical structure. It all depends on the physical structure of the component. So in chapter 2, chapter 3, and chapter 5, we look at them separately. In chapter 6, we're going to combine these three components into one circuit. All right. So now let's look at C again. Okay, let's look at the notes again. So when current increase, the change in current DI is positive. If DI is positive, okay, if DI is positive, then induced EMF is negative because it is to oppose the increasing in current. If your DI is negative, then induced EMF is positive. Okay, positive, negative, negative, positive. You yourself have to memorize these two statements. Okay, you have to know these two statements. Why? Because when it comes to questions, when it comes to examples in your books, in your tutorial, you're not given the sign convention. You yourself have to know what is a sign, okay, which sign to be used in your calculation. So soalan tak akan bagi kamu sign convention. Okay, next, by comparing EMF equals to negative N d phi over dt and EMF equals to negative L di over dt, okay, we then obtain an equations Li equals to N phi. Rearrange the equations. L is also equals to N flux over I. Okay, N flux at the same time it represents magnetic flux linkage. Therefore, it could be capital letter phi over I. Okay, so this is a very important part. Make sure you take note or you can highlight it in your books. Okay, so N phi is equals to flux. So L at the same time is equal to flux linkage over I. So it is a scalar quantity and the unit is Henry. The values of the self-inductance, it depends on what? So by looking at these equations, actually you can tell as well. You have L equals to N flux. Oops. N flux. Okay, N flux over I. N represents the numbers of turns. Okay, so it affects the values of your inductance. And then mu naught, okay, mu naught is coming from where? Okay, it's coming from your B. Why? Because L is equals to N flux over I. And at the same time, it is equals to N. Now, flux is BA cos theta over I. Okay, and then what happens right here? Well, it depends on B after this. It depends on whether you're looking at the coil or you're looking at solenoid. If you're looking at the coil, remember what is the B for coil. So B coil, the ones that you learn in chapter 4, it is mu naught Ni over 2R. If you're looking at solenoid, B solenoid is then equals to mu naught Ni over L. Okay, so that's why I told you before, you need the information, the knowledge from chapter 4 in order to answer the questions in chapter 5. Why? Because you need magnetic field, especially for coil and also for solenoid when it comes to the induction process. So substitute into the equations, you will see that now you have a mu in your equations. So it depends on your inductance, also depends on the mu, the permeability of the medium in the coil. Why? It's coming from the equations of B. Okay, so when you plug it in, you will see that other than N, other than N, it also depends on the mu. Okay, mu naught. We use mu naught because we assume it's vacuum. But in reality, you can place soft iron core or any other conductor inside your solenoid. And different medium, different material, you will have different mu naught. Okay, and the last one, of course, is the size because you're looking at the area and also the radius or the length. Now, where is the I? Now, I is gone after you substitute into the equation. Meaning that your inductance, it does not depend on current. Okay, it does not depend on currents. So, which means it's actually it obeys what happens in the definition. Because definition say it is just a ratio, EMF over di over dt. Okay, so di over dt, the change in current, it won't affect the values of L according to the definition. So in our derivations here, after you derive it, you will see that L for coil is equals to mu naught N square A over 2R, and the L for solenoid, okay, the L for solenoid is mu naught N square A over L. The I is gone, which once again, it shows you it does not depend on the current. Change in current, it won't change the values of L. All right, so that is how you obtain this, okay, this set of information. So self-inductance depends on the size or the shape of the coil or solenoid, and then the numbers of turns, and then the permeability of mediums of the coil. So a circuit which possesses mainly self-inductance is known as inductor. Okay, and it is used to store energy in the form of magnetic field. So in chapter 2, capacitors store energy in the form of electric field. In chapter 5, inductor store energy in the form of magnetic field. So both components, we use it to store energy. Just that one you store it in electric field and one you store it in magnetic field. Okay, so the symbols of inductor in the electrical circuit is this one. So self-inductance in the coil and the solenoid here. Okay, I derived it for you just now. So right now you just have to write down the equation. Okay, you just have to write it down. So L is equals to mu naught N squared A over 2R. Here is L equals to mu naught N squared A over F. Okay, mu naught N squared A over F. So this one, you just write it down. Okay, you just write it down. So, yes, here I give you a, wait, oops. So I give you 2 minutes. Okay, I give you 2 minutes to write down a bit of summary right here. Okay, actually, I would say this is quite a good summary to tell you what happens in all 3 components. All right, because you're going to need it, especially in your UPS 2 after this. Okay, UPS 2 nanti dah kena uji lah benda-benda ini. Okay, contohnya ini. So you can write down the summary. I give you 2 minutes to write it down. Okay. Oh, yeah. For these 2 equations, okay, the equations in the red color, you yourself have to memorize it. It won't be given in the exam. Okay, dalam exam dia tak bagi. So these 2 equations, you yourself have to know. Okay, well, either you memorize these 2 equations straight away, okay, or you learn how to derive it based on the equation given in the list of formula. Okay, so this equation is given, this equation is given, these 2 equations is given in your list of formula. So either you memorize these 2 equations, the equations in the red color straight away, or you follow the step that I show you right here. Okay, you derive it by yourself. The important thing is you have to know whether the B, okay, or the inductors that you calculate is for solenoid or for coil. So for coil, then you need to use the B for coil. If solenoid, then you need to use the B for solenoid. Okay. So now let's go to a 5.4. Okay, 5.4 is just a derivations. Okay, what am I going to do? I'm just going to read through it quickly. Okay, because I'm not going to waste too much time on derivation. You yourself can go through it when you're free. So consider an inductor of inductance. L supports that at time C, the current in the inductor is in the process of building up to its steady value at the rate of di over dt. Now, the reasons why di over dt, because it keeps changing with time. It is unlike your resistor. What happens in a resistor? The moment you switch on the power supply, the I straight away, it will flow through the resistor, okay, without any issue. Okay, the value across the resistor is the same. What happens in an inductor? Okay, in an inductor, initially you have a current flowing through it. But what happens? It will experience induced I's in the opposite direction. So it's actually building up slowly. Okay, it's built up slowly. Okay, over a period of time. Okay, it's unlike a resistor. The moment you switch on the power supply, then the I in every single component is the same. But when it comes to resistor, it comes to inductor, it will take time. Okay, initially you have I and then I induced in the opposite direction. So the I on the right hand side, okay, this is initial state. Okay, initial state. So this is your I minus I induced. And then after a while, okay, after a period of time, it will then become a constant value. Okay, so you have I here and I here. So at this time, your I induced is equal to 0. Okay, after a moment. So it is unlike resistor. Okay, there is a slight difference. That's why, okay, that's why in this statement here, it says the current in the inductor is in the process of building up to its steady value. So initially, it is not equals to I yet. All right, so it will be equals to I when now it's become a constant value, okay, after a period of time. So the magnitude of the back EMF is given by EMF equals to L di over dt. Now the negative is it's not including in this equation. Why? Because you are looking at just the magnitude. Okay, in your calculation, in case you got a negative value, then always add an additional sentence to rewrite it in terms of magnitude in a positive value. Okay, kalau kamu dapat nilai negatif di hujung sekali, nanti Anda tambah satu ayat, tulis the magnitude of EMF. Induced EMF is, okay, then you write down a value without negative sign. Okay, because usually questions will ask you to calculate the magnitude. So the electrical power in overcoming the back EMF, then of course, if you're looking at back EMF, P is equals to, okay, this would be your I induced and also your EMF induced. Why? Because now you're looking at P induced. So they all must be coming from the same family. Okay, they all must be coming from the same family. So P is then equals to Li di over dt. P di equals to Li di. Rearrange the equation. Now this part, okay, this part is equals to energy. Why? Because power at the same time is equals to energy over time. This is the equations that we learned in SEM 1. So it is equals to Li di. So you replace here P dt as a du, your energy. Okay, then what happens? You integrate both sides. So the total energy stored in the inductor has increased from 0 to I. Okay, initially in your inductor, it has no current. After you switch on the power supply, it builds up slowly. And then when it comes to I, okay, then it can be found in the integrating equations. So it then equals to U equals to 1 over 2 Li squared. Okay, Li squared. So for a long, for a long air core solenoid, self-inductance, actually the I is coming from the normal I. Okay, it's coming from a normal I. So you have to just be back EMF. Because as it becomes steady, the I flowing through it is equals to I. Okay, through inductor. So when it is at a steady state, after a while, we use I instead of I induced. Okay, so I. So I times EMF induced. Okay, kamu take note sikit di sini. This is your I. Okay, and then this is the power to overcome induced EMF. So P induced equals to I, the steady I, times induced EMF. Okay, induced EMF. So for a long air core solenoid, the self-inductance is, okay, L equals to mu naught N square AL, and then you substitute into the equations. So energy stored in the solenoid. So once again, this equation is not given in the list of formula. You yourself have to derive it. Okay, you yourself have to derive it. If question asks you to calculate energy stored in solenoid by using the information right here. Okay, over L. So half mu naught N square AI square over L. So that is the energy stored in solenoid. So here you actually have a square. Tak nampak kan? Okay, U equals to 1 over 2 Li square. Okay. All right. So write down the equations. I give you 1 minute to write down the equations. Then we'll go to the mutual induction process. Actually, it takes more time than expected. So today we're just going to finish off chapter 5. Okay, we're going to finish off chapter 5. So 1 minute for you to write it down. Then we'll proceed to mutual induction. All right. Now let's look at mutual inductance. Okay, so yeah, I got a message coming in. Okay. So mutual induction is defined as the process of producing an induced EMF in one coil due to the change of current in another coil. Okay, due to the change of current in another coil. So consider two circular packed coils near to each other and sharing a common central axis. So common central axis means here, okay, they have the same center. Okay, they have the same center. That is a common central axis. So as the current I1 flows in coil 1, it will produce, okay, it will produce a magnetic field as shown in the figure right here. Okay, so if you look at the diagram here, we have two coils. Okay, we have two coils, coil 1 and coil 2. So coil 1, sometimes in questions, they call it primary coil. Okay, primary coil. And coil 2, we call it secondary coil. What is the main difference between primary and secondary? Primary coil is the one with power supply, with battery. Secondary is the one without. Okay, so if you look at the diagram right here, they put a galvanometer here because they just want to show you the directions of the induced current flow. So what happens right here, the moment you switch on the power supply, magnetic field will be generated in the primary coil. The one with current is the first coil, is a coil 1, is a primary coil. It will have magnetic field. And because now the second coil is placed close to your coil number 1, so the field line generated by I1 will also pass through your coil number 2. So the field lines that you look at right here, okay, you look at it right here, they are all coming from your coil number 1. Coil 2 itself, it doesn't have any magnetic field. Okay, it doesn't have any magnetic field. That's why if you look at the definitions of mutual inductions again, it says it is a process of producing an induced EMF in coil 1 due to the change in another coil. Any changes that you make on the coil 1, it will affect your coil 2. Okay, it will affect your coil 2. That is the reason why we call it mutual. Because this process, it can happen if you have just one coil, right? So if current I1 changes with time, the magnetic flux through coil 1 and coil 2 will change with time simultaneously. So both of them, they will change. Due to change of magnetic flux through coil 2, induced EMF, okay, and EMF is induced in coil 2, according to Faraday's law. Now, actually, not just in coil 2, both coil, they undergoes induced EMF, they undergoes induction process. Just that coil 1, it undergoes self-induction process. Coil 2, it undergoes mutual induction process. Okay, coil 1 undergoes self-induction because it has a battery and the changes is happen inside itself. So this one is self-induction. Okay, self-induction. Coil number 2, this one is because of the neighboring. It doesn't have a battery. It happens, okay, it has a EMF because of changes in coil 1. So coil 2, it experiences mutual induction. Okay, it experiences mutual induction. So that is the difference between these two diagrams. Okay, these two coils. So in other words, a change of current in one coil, it leads to the production of an induced EMF in the second coil. That's why we call it mutual induction. Okay, that's why we call it mutual induction. So at the same time, self-induction occurs in coil 1 because the flux through it also changes. Okay, because the flux through it also changes. So that is your mutual induction. Okay, so how are we going to determine the direction? Okay, your books, let me see. Oh, your books, they doesn't give you the diagram. So now let us draw a simple diagram. Okay, kamu punya buku, dia tak bagi kamu diagram ini. So now let us draw a simple diagram. So this is your first set. Okay, this is your second set. How are we going to determine the flow? Okay, so usually we will put a galvanometer right here, tell us what is the directions of current flow. Okay, so again, I have it right here. 3, and this is the second coil. Okay, so primary coil and the secondary coil. This one, the first one, what am I going to look at? I'm going to look at what happened when I increase first. Okay, when I increase. And the second case would be I decrease. Okay, the first one, actually you have a current flowing in the clockwise direction. How do I know? Based on the terminal of the battery. Okay, and then when the current is flowing in this direction, okay, now I'm going to assume, okay, because my diagram would, it's going like this, the current, okay, is flowing. So when it's at the front of the solenoid, the current, the finger should be going up, meaning that now I have north pole on the right, on the left-hand side, and south pole on the left-hand side. Okay. North, and south pole on the right. Okay, so both primary coil, they started from the same directions, they have the same pole. Okay, no. So this is I increased and I decreased. So north pole on the left, south pole on the right hand side. So what happens right here, meaning that initially I have magnetic field line like this. Okay, and this magnetic field line at the same time is flowing through your coil number 2. So this is your B. Okay, the B in both cases. So meaning that by looking at this diagram, we can then determine the pole of the secondary coil as well. By looking at the diagram, now I have B from right to left, meaning that initially the north pole and the south pole is same as your primary coil. Okay, north on the left hand side, south on the right hand side. That is what happened initially. Okay, that is what happens initially. So after that, what happened? Now my I increased. When my I increased, B increased. If B increased, okay, if B increased, the opposite direction will be induced. Okay, B induced is pointing towards opposite direction. So right now, if you look at second coil, what happened? If you look at second coil, now I have south pole induced on the left-hand side and north pole induced on the right-hand side. So by using south and north induced, okay, south induced and north induced, I can determine the direction. Okay, I can then determine the directions of the secondary coil. So based on the north induced pole, okay, I found that my I induced is flowing in the anti-clockwise direction. So what is my galvanometer? The needle is being deflected to the right. So that is what happened in secondary coil. When I decrease, magnetic field induced will be generated in the same direction, meaning that now my north induced and my south induced, they are located at the induced. Okay, so this is my I induced. So when it flows through the galvanometer, the needle is being deflected to the left. The needle is being deflected to the left. So now I give you 2 minutes, well, actually more than 2. I give you 5 minutes to sketch the diagram here, okay? So that you know how to determine the directions of induced current in your secondary coil. And also, what is the deflections of the galvanometer? Because this is a very often seen question in your exam. Soalan sangat suka tanya Anda, dia deflect ke kanan ke kiri. So macam mana kamu nak tahu? That is how you know. That is how you determine it. Okay, that is how you based on whether the I increase or decrease, and then from there you determine the directions of B induced. Once you have that, okay, then you can determine the directions of the current flow. And by using current flow, you will know that whether the galvanometer is being deflected to the left or to the right. Okay, so 5 minutes for you to sketch the diagram. Then we will look at the calculation. Okay, we'll look at the equations. we'll just finish it off. Okay, then later on you can refer to the videos to sketch the diagram. Okay, the diagram is very important because it's one of the popular questions in your exam. Okay, now let us look at the equations. Mutual inductance. Mutual inductance is defined as the ratio, and again, the ratio of induced EMF in coil to the rate change of current in another coil. Okay, in another coil. So meaning is that when it comes to the equations, the things that you have to be careful is a subscript. So let's look at the subscript. Consider coil 1 and coil 2, they have N1 and N2 turn respectively. If coil current I1 in coil 1 changes, the flux through coil 2 will change, and therefore induced EMF is being generated in coil 2. So induced EMF is in coil number 2. Therefore, if you look at the equation, the subscript for EMF is 2. But then this EMF is induced due to the change in 1. So you use I1 in the calculation. Coil number 2 itself, it doesn't come with I. It doesn't have. Okay, so you use EMF 2 and I1. So EMF 2 equals to dI1 over dt. So the equations is EMF 2 is then equals to negative M dI1 over dt. And M is a constant value, provided if you are keeping the same coil, same solenoid in your question. Okay, so you can change the power supply, you can change any other things, but as long as you're using the same coil with the same material, same medium, and so on, same physical structure, then the M is a constant value. Inductance, mutual inductance is a constant value. So if vice versa, and the induced EMF in coil 1, now if your current is now in coil 2, then induced EMF will be produced in coil 1. So EMF 1 is then equals to negative M dI2 over dt. So the I must be coming from neighbor. Okay, the I must be coming from neighbor. It cannot have it inside itself. So from the Faraday's law for coil 2, okay, you then derive the equations and you will obtain an equation that is very similar to the self-inductance just now, which is M is now equals to N2 phi 2 but over I1 equals to N1 phi 1 over I2. Okay, so it depends on where is the current. When it comes to mutual inductions questions, you try to identify the coil with the current first. Okay, if current is in coil 1, then all the other information must be coming from the other coil, the second coil. If current is in your coil number 2, then all the other informations, the N and the flux must be coming from coil 1. Okay, so that is the equations, and that is how we use it. Okay, that is how we use it. Okay, now next question, okay, next subtopic, which is the last part in the chapter 5, mutual inductions. Okay, mutual induction, coaxial solenoid overlapping with each other, as shown in the diagram. Okay, overlapping with the same cross-sectional area and so on, and then they share the. Okay, they have the same central axis. So when they're overlapping with each other, when current I1 flows in the primary solenoid, it produces a magnetic field B1. But because they're overlapping with each other, okay, so two of them, they will have the same field line passing through it. Okay, same B passing through it. So in this case, when they're overlapping, we say no flux leakage. Because remember, flux, it depends on the numbers of field line passes through the cross-sectional area, the surface area. If they're overlapping with each other with the same A, then both of them, they will have same magnetic flux because they have same amounts of field line passes through the same cross-sectional area. Okay, so that's, in that case, we say no flux leakage. If you place them side by side, okay, if you place them side by side, then this case, we say flux 1 is not equal to flux number 2. Okay, it experiences a so-called flux leakage. Why? Because the amount of field line passes through both coils, they are not the same. Okay, you will have more field line passes through your coil 1 compared to the second coil. Okay, so for example here, you have 3 lines passes through your coil 1, and then you have just 1 line, okay, passes through your coil number 2. So meaning that flux 1 is not equal to flux 2 if you place them side by side. Okay, so this is a crucial part in a question as well. Sometimes questions will tell you, you place two of them coaxially. Coaxially means they are overlapping with each other. Okay, so then the flux in the coil 1 and the coil 2, they will have the same value. Okay, they will have the same value. So if the current I1 changes, EMF is induced in the secondary solenoid. Therefore, the mutual inductance occurs and it gives you the value, and same value if you derive the equations. Okay, if you derive the equations, M is equals to mu naught N1 N2 A over L. Okay, over L. Now, when it comes to mutual inductance, okay, in a previous page, let's see. Wait, I need to scroll back. Okay, here one thing is missing. When it comes to mutual inductance, actually it doesn't matter whether you're looking at coil 1 or coil 2, they will have the same mutual inductance. They will have the same value. Okay, so M1, the coil 1, coil 2, they will have the same mutual inductance. Therefore, we just use M in our calculation. Okay, so that is the equations if you put them coaxially. M equals to mu naught N1 N2 A over L. Okay, mu naught N1 N2 A over L.